Okay, so we're going to look at the intersection of three planes, except for this time we're going to look at when they don't intersect and when they intersect. Okay, so we had a situation in the last one where the three planes did not intersect, and they would have formed something like this. So planes coming out of the page looking like that. And we also had a situation where they did intersect, where this plane was not here, it was right in the middle. So it intersected at a line, the line comes out of the page like that. And then we had the intersection of the three planes where they would intersect at a point. And that is one specific case that we want to look at in a different way. But first of all, we have to look at all the different situations. So if they don't intersect, we have this situation here, or we could have the three planes parallel, so coming out of the page parallel, or we could have two of those planes are coincident, and it's just two planes parallel. Then we could have the situation where there's two planes that are parallel and another one crosses them like that. There's no single intersection point for those three planes. And in all these situations, if we look at these, so it includes a situation where there is an intersection but only a line of intersection. If we look at the normals for these planes, they're all coplanar. So these normals are here. They all lie in the same plane. And this one here, so the normal there, and normal there, all lie in the same plane, and same with here. They all lie on that page. The only time when the normals are not coplanar, they don't lie on the same plane, is when you have a point of intersection. Okay, so in that situation, we have a calculation that we can do to determine that. But we're going to go take a step back here, and we're going to look at the formula, or the formula that we used for the volume of a parallelepiped formed by three vectors. So if you had three vectors, there's one, there's another one, okay? These two can form a parallelogram, right? And then take a third one, and it comes out of the page kind of like that on an angle. That vector would then, okay, you could use that to then form a parallelepiped. And it looks something like that. Okay, and so on. So you'd have a parallelepiped. If you did the triple scalar product, which was, so say that's U, V, and W, so U cross V dot W, that gave us the volume of that parallelepiped. And that was a nice formula to get. Now, if these three vectors, U, V, and W, are all on the same plane, then that parallelepiped has no volume. So if it has no volume, then this triple scalar product is going to equal 0. So in all these cases up here, where the normals are coplanar, the triple scalar product of those normals is going to be 0, because they're going to give you a parallelepiped with 0 volume. The only time when you're going to get a non-zero volume for the parallelepiped is if these vectors are not coplanar, or if you're thinking of the normals, they're not coplanar. Okay, so here's what I've written out here for you. So the triple scalar product, n1 cross n2 dot n3, gives the volume of a parallelepiped formed by the three vectors. If the three vectors are coplanar, then the volume is 0. This is just what we said. There will only be a single intersection point of three planes when the normals are not coplanar. So therefore, when the triple scalar product does not equal 0, there will be a single intersection point. Okay, so when the triple scalar product is not 0, there is a volume, and the normals are not coplanar. So that means you're going to get an intersection point. Okay, so we can check this with the example A that we did. So in the last video we had example A, and we had these three normals here as our normals for those planes. If you do the triple scalar product with that, you end up getting 23, which is not equal to 0. And in that, we got a single intersection point, so this verifies that we were going to get a single intersection point. In the other examples, we got a line of intersection and no intersection. So for those ones, we should get a triple scalar product that is 0, because the normals should be coplanar. And that's actually the way I chose them. So let's check it with the three normals. It's the same in both example B and C from the last video. So if we do the triple scalar product, you end up getting 0. Okay. So you get 0, which means there is no single intersection point. It doesn't guarantee that there's no intersection line, but it tells you that there's no single intersection point. Okay, so that's it with the triple scalar product. Now we're going to look at a question, page 531, 8b, where it asks you to find the intersection of three planes. And I'm going to use matrices to do this. So it's another method for doing this. So here are the equations of the three planes. And I'm going to write this down in matrix form, which means just remove all the variables and keep this organized in terms of coefficients of the variables. Okay, so this is what I've done here. So the coefficient of x here is 8, so I put 8 there. 2, 2, 1, 1. And the coefficients of y are in this column. Coefficients of z, this column. The dotted line represents the equal signs, and on the other side of the dotted line are the constant values. We're calling this row 1, row 2, and row 3. Okay, so we can do with rows what we used to do with equations. We can multiply a row by a number and add it to another. We can subtract rows. We can divide rows by a number, and so on. So this sort of helps us keep it organized a little bit. So what I'm doing here is I want to get rid of I want to eliminate the x in the first one and the second one, and because this is a 1 here, it makes it easy to multiply row 3 by 8 and then subtract row 1, or by 2 and then subtract row 2. You've got to multiply the whole row though. Okay, so I'll write it out here for you. So the new row 1 then becomes row 1 from here minus 8 times row 3. Okay, so 8 minus 8 times 1 is 0. Negative 6 minus 8 times negative 2 is going to give you 10. 24 minus 8 times 3 is going to give you 0. 21 minus 8 times 2 is going to give you 5. That's our new row 1. Do the same thing for row 2, except for you're multiplying row 3 by 2. Subtract them, and you'll get these values in here. Now we've eliminated the x value here, and conveniently eliminated the y value here. However, if we didn't eliminate that there, then I would multiply the new row 1 by 6 and the new row 2 by 10, or reduce that, and multiply it by lower numbers, and then eliminate the y's. Once you got that, then the y in one of them, then you'd have 2 zeros in a row and just a single constant, which is the z coordinate, or the z coefficient, and then you could solve for z. Now we just have in row 1 the y coefficient, so we can rewrite this equation out. 10y equals 5, or y equals 1/2. Now you can sub that, so that's from row 1. Now you can sub that into row 2's equation, which is 6y minus 9z minus 24. Sub that in there, and you get z equal to 3. Okay. Sub the two of them into the third equation, row 3, and you get x equal to negative 6. And therefore you have a point of intersection which is negative 6, 1/2, and 3. So that is using matrices to solve it.